Hello, guys. So, this is the fourth lecture of economic geology, and this lecture will start with ore textures and structures mainly. So, let's start. Ore textures and structures are kept key aspects of mineralogy and geology that help scientists understand how ores formed and how they can be extracted. Okay, so ore textures are very important phenomena. We use optical again microscopes, um, and we look into the microscope. We look into thin sections. This ore sections are made in a slightly different way as we have studied mineral thin sections. So we do not have pleochroic and double polarized light in this kind of things. So we use mostly refracted microscope, refracted ray microscope for ore texture studies and structures, and mostly a fragment of a ore piece or ore sample is taken. We smooth out the top and the bottom surface, and then we use refracted rays microscope to study those ore sections. So ore textures are the characteristic of mineral crystal and their arrangements within the ore body. Okay, so it is the characteristics of mineral crystals present and their arrangements within the ore body. So now we talk about the types of primary textures. So we have crystalloblastic, that is again equigranular texture where minerals are crystalline and formed by slow cooling. Okay, so we have well formed crystals with well formed edges and sides. So obviously it will form in a slow cooling process. Example is a metamorphosed ore. Okay, so then we have idioblastic or euhedral. The crystals have well formed faces indicating growth in open space. Again, slow cooling. Subhedral crystals are partly bounded by crystals. The same thing: euhedral, subhedral, and anhedral. Okay, so partly will be subhedral, anhedral will be lack perfectly formed faces, often intergrowth or restricted in growth. Okay, then we have poikilotic texture, similar to igneous textures. So large crystals enclosed smaller ones, often in igneous rocks. Now we have open space filling. So open space filling is a slightly different thing that you have might have not studied in metamorphic or igneous textures. So we have zoning. This is the same concentric growth bands. Then we have coliform structures, that is botryoidal or layered appearance from colloidal deposition. Colloidal deposition means colloidal solutions when they deposit um, minerals, they will form this botryoidal or tree-shaped structure. Botryoidal means it will form, like cauliflower. You have seen cauliflower flower vegetable, so it will look like this. There will be branches, and then there will be structures like this. Bulbous cauliflower shaped structures will be there, and there will be. So this is type of a cauliflower shaped structure or botryoidal structure, or bulbous. Sometimes bulbous type of structures will also be there. Bulbous structure. This is also botryoidal structure. So coliform texture or botryoidal layer appearance, we have coliform texture. Then we have comb texture, that is prismatic crystal growing inwards from vein walls. Okay, comb texture look like just like a comb, so it will look like this. So this is the fracture area, and you will have needles of combs like this. Okay, from the outer wall towards the core of the fracture. It will be okay. It will start from the outer wall and will slowly propagate towards the core of the fracture zone. This is comb. We also have diagrams, so don't worry. Then this is plastification or rhythmic layering due to changing fluid condition. So there will be rhythmic layers due to changing fluid conditions. You will have one on another, separating different changing conditions. So these are the structures. This is zoning. This is some common thing that you have already studied. This is the coliform texture forming bulbous type of structures like this. This is the section or cross section of a coliform structure or the inside of a coliform texture. Okay. If you are not understanding this diagram, then just let me know. I will send some other diagrams of coliform texture in the Telegram group. And this is comb texture. Okay. So you can see from the outer lining it will start propagating. It will reach the, if it's completely filled, it will be like this. And then crustified veins, you have different layers starting from the walls and going towards the core. Now we'll talk about the secondary ore textures. So these results from post depositional changes. Okay. So after deposition of the rocks, there will be post depositional changes, and that will result in certain kind of textures like replacement, deformation, cooling, and weathering. All this will results in this secondary ore textures. Now, types of secondary textures. So we have replacement textures. Obviously, if there is any fluid which is say passing through a rock, it may alter some of the minerals. So we have pseudomorphs. New minerals replace old ones but retain the original shape. Okay, it will retain the original shape, but minerals will alter. Pseudomorphs. Then we have cusp and caddies. So irregular boundaries between replaced and replacing minerals will take place. Then boxwork texture, very important. Cellular pattern from oxidation. It resembles random crisscross lines. Example goethite replacing pyrite. Okay, so like this crisscross lines will be there. So this is not a ideal example, but I have shown you how this will look. But if I get a good picture of boxwork texture, then I will again share it with you. So again, boxwork texture is there. Cellular patterns from oxidation. It resembles random crisscross lines. Example goethite replacing pyrite. Then we have cooling textures. So exsolution. Exsolution is a process where a homogeneous solid solution becomes unstable during cooling and separates into two distinct minerals phase with different composition but similar structures. Example perthite. You already know this in igneous petrology. I have discussed this how perthites form or how antiperthites form. This again the similar picture. Okay, orthoclase is the host and albite is the lamina. So albite versus anorthite. So recrystallization will happen, new crystals form, growth from the thermal changes. Because of temperature change, this will happen. Then again, deformation textures like twinning, cataclastic, and brecciation. Twinning, you already know, symmetrical crystal intergrowths from stress. This is twinning, starlight twin or cruciform twin. Okay. Then we have cataclasis, crushed ore minerals due to tectonic stress. So we have cataclasis like this. Okay. Then we have brecciation, angular fragments due to tectonic forces like this. Angular fragments will be there. Okay, brecciation. And annealing, that is grain boundary smoothing from heat and jointed materials. So because of heat, there will be grain boundary smoothing. There will be smoothing of the grain boundary and they will get joint. Okay, joined together, forming jointed material. That is called annealing. That can also happen. So all these are secondary textures formed after the, or you can say post deposition, after deposition or post deposition changes are the secondary or textures. This is a pseudomorph texture. Okay, pseudomorph. Okay, now ore structures. So we'll talk about ore structures. So ore structures describe the physical arrangement of minerals within the ore body and how they can relate to the surrounding geology. Okay, so ore structure means if the ore is, say, disseminated throughout the rock, or is it present in veins, or is it present strata bound, a single strata will contain all the minerals, or is it discordant like a dike? Okay, it can be anything. It can be porphyry copper, a humongous structure of copper deposit within the host rock. So how the host rock is how the uh, ore body is present inside the surrounding rock or the host rock is how we will discuss uh, in the ore structures. Okay. So it is mainly of two types. What is concordant? Concordant means it is in uniformity with the stratas that were formed, and discordant. Discordant is often which is cross-cutting the already formed stratas. Stratas means the already formed layering of the rocks. So discordance is mostly considered, or always, discordant rock bodies or discordant ore bodies have formed after the deposition of the, after the, like, post depositional changes or post depositional structures will give rise to ore bodies that are mostly discordant with the original country rock, whereas concordant ones are mostly formed during the formation of the rock. Now, so, or we have the concordant discordant is the main major types. Then we will discuss one by one. First is the vein type, vein structures. Description: ores are confined to narrow linear fractures or veins within the host rock. So we have some fractures here, and when a liquid pass, it will start precipitating all minerals here, and then it will be filled. This is the vein type deposit. Okay, ore vein, and this is the host rock. Surrounding rock is the host rock, and this is the ore vein that we will be interested about. So formation forms when mineralizing fluids fill fractures, typically in hydrothermal systems. Example: gold veins or quartz veins containing sulfide minerals. Right? So most of sulfide minerals and quartz veins and gold veins are important for vein type deposits. Okay. Then we have disseminated ore structures. So ore bodies are scattered throughout the host rock in small amounts. Okay, formation is occurs when mineralization is widespread but occurs in small concentrations. Okay, example: copper or gold in porphyry copper deposits. So we have disseminated one. See, this is disseminated. Dissemination is throughout the host rock, it will be spread. Okay, the ore bodies will be spread throughout the host rock, and you cannot delineate a particular polygon, a particular structure to delineate the ore body. Okay, so it is mixed up with the host rock. So mostly we get copper or porphyry copper deposits and or gold. Okay, these are the things that we get from disseminated ore structures. Very good example is porphyry copper. Then we have massive ore structures. Description: ore minerals forms a large solid mass with minimal variation or zoning. Okay, typically occurs in environments where mineralization is concentrated in a specific area due to high fluid flow or high pressure. We have nickel, copper in magmatic deposits, giving massive ore structures. This is a massive ore structure. Massive ore structure will be, look like this. Say, for example, so massive ores are mostly they have do not have a particular layering. Say this is a maybe our area of interest, and there is a huge body of a massive ore body. Okay, this is not concordant with with the original rock layer. Okay, sometimes batholiths form this type of massive ore bodies. So we have massive ore bodies, and the ores are present inside this massive body. Massive means it is not layered. Okay, massive, massive body means not layered. So nickel, copper in magmatic deposits are good examples of massive ore structures. Okay, now then we have stockwork structures. So description: ore is found in a network of intersecting fractures or veins. This is a stockwork, intersecting fractures and veins. This is actually n echelon, say n echelon structures. Okay, this is called n echelon structures, S-shaped veins or fractures, and which will be often connected to each other. Forms when mineralizing fluids fill a network of fractures in host rock, often in hydrothermal systems. So this type of stockwork structures are often associated with hydrothermal systems. Okay, hydrothermal systems, when this um, metals carried by uh, upward drafting liquid or fluid that will flow through these fractures and precipitate and forms this type of stockwork or mineralization. Examples are gold in epithermal systems. Gold in epithermal systems are classic example of stockwork deposit. Then we have replacement structures. So ore minerals replace or substitute the original minerals of the host rock. Okay, so replacement structures are most associated with contact metamorphism. This is a contact metamorphism type. It occurs when mineralizing fluid percolate through the rock and chemically replace existing minerals. So say this is a batholith which is in contact with the country rock, then fluids will migrate from here, okay, due to cooling, and then they will alter the country rock. So limestone replaced by zinc or copper in skarn deposits, often associated with contact metamorphism. Fine. Now we have talked about structures. Now we'll talk about importance of studying ore textures. What are the importance? Okay. So understand the timing of ore mineral formation. We can understand if this is post depositional, pre depositional, or syn depositional. Textures can reveal whether ore minerals formed before, during, or after the formation of host rocks and associated geological structures. Then we can determine the sequence of geological events. Okay, so which texture or which ore body formed first, which formed later. Okay, so we can define the sequence, like how the story tells us. Okay, by examining overprinting relationship, sometimes one mineral can overprint another mineral. So that times we can understand that this mineral has formed after a certain mineral has already formed, and there is a replacement relationship there. So overprinting relationships, deformation features, sometimes they can get deformed, they can get folded. Okay, and minerals growth patterns, geologists can reconstruct the depositional history. Okay, depositional history can we can develop, and we can also define the post depositional process within an ore body. Then we have estimate cooling rates and cooling rates or mineral accumulation rates. So certain textures such as zoning, exsolution, or crystal size distributions provide information about the thermal history and rate of crystallization or precipitation of ore minerals. Fine. Then identify equilibrium mineral assemblages. So recognizing minerals that formed under stable conditions allows for the application of phase equilibria and geothermometry. Geothermometry means to understand the temperature relationship of the different minerals. This is crucial for interpreting the pressure temperature condition during mineral formation. So we can understand the geothermometry also. We can also understand sometimes the geobarometry. Barometry means to understand the pressure study. Okay. Thermometry means temperature study, and barometry means pressure study. So this lecture will be very important. Okay, many a times a lot of question has been asked about ore textures. This is a very favorite topic for examiners. So if you are not understanding in the first attempt for this lecture, I would suggest you to look uh, like watch this video more than maybe 2 or 3 times, then make notes, make proper diagrams, short notes, and then you will able to understand it in a better way. Now, stratiform and strata bound deposits. Okay, so we'll take one by one all the types of deposits and then we will describe it. Stratiform and strata bound means You can see strata bound, mean that is the ore is emplaced only in a particular strata and nowhere else. Okay, so it is bound to a particular strata, particular layer. Definition: stratiform deposits are layered mineral deposits that are comfortable, that is conformable. Okay, conformable means it is not cross cutting with the bedding of the host rock. They form at the same time as the enclosing sedimentary rock. They are formed, so that is syngenetic, as they are formed at the same time as the enclosing sedimentary rock, meaning they are syngenetic in origin. Okay, so their origin is syngenetic. That means they are formed at the same time as the time the rock has formed. So you can see this is the anorthosite layer and this is the chromite layer. So chromite layers are concordant with the anorthosite layer as well as the gabbro-olivine diorite and anorthosite layer. Now we have olivine cumulates here plus pyroxene plus dunite layer. So this is the chromite layer that we are interested in, which is concordant with all the layers present. That is strata bound. That means it is only present in a particular strata and not in any disseminated form or in any other form. Okay. So any ore body that is bound to a particular strata, a particular layer, we will call it as a stratiform or a strata bound deposit. Okay, this is very simple. So this is again a stratiform simple figure. You can see these are lenses present only in a particular strata, and it is not cross cutting anything, not a massive body also, not in veins also, but just present in a particular stratus. So parallel to the host rock strata, okay, deposited during sedimentation, it is syngenetic, typically uniform in thickness and lateral extent, often found in sedimentary or volcanic sedimentary sequences. Okay, examples are banded iron formations, very good example of strata bound deposits, BIFs found in Karnataka, example Kudremukh, Jharkhand, Odisha, we get these BIFs. These are ancient marine chemical sedimentary deposits, right? Then we have SEDEX deposits. SEDEX have sedimentary exhalative SEDEX deposits. We have lead zinc deposits like those in Java regions. We have Cooper Schiefer. This is Cooper Schiefer. Cooper Schiefer copper deposits in Europe, example Poland, that is also stratiform in nature. So we get SEDEX deposits of Java, we get Cooper Schiefer deposits of England, of Poland and Europe, stratiform. Then we have in Kudremukh, that is in Karnataka, we have BIF deposit. Okay, so if you're writing, just write BIF of Kudremukh, Kupashifa, Poland, and SEDEX of Zavar, right? Then we have strata bound deposits. So strata bound deposits are mineral deposits that are confined to a particular stratigraphic layer. Okay, previously we have discussed stratiform deposits, a layered mineral deposit that are conformable with the bedding of the host rock. And then we have strata bound. That means stratigraphic layer, but not necessarily deposited at the same time as the host rock. Okay, the strata bound can be syngenetic, can be post genetic, but stratiform is always syngenetic, right? This is the difference between the two. So they are often epigenetic, formed after the rock, and are restricted to specific rock horizons due to structural or chemical controls. You can see this is the sediment, this is strata bound ore bodies, but that will be only be present in a particular strata. The replacement will already all replacement or any kind of new addition of minerals will already be confined to a particular strata. Again, strata bound is can be syngenetic, it can be epigenetic or postgenetic, whereas stratiform can only be syngenetic in nature. So key features are confined to a specific bed or layer, may cut across bedding locally but restricted to certain strata, controlled by permeability, porosity, or chemical reactivity of the host rocks. Examples are copper deposits of Malanchkhand, okay, Though structurally controlled mineralization is localized in certain ethological units. So they have some epigenetic deposits also which are strata bound and some structural deposits also. But yes, we can give example. They have some strata bound deposits. Then we have lead zinc deposit of Rampura Agucha, that is in Rajasthan, hosted within the specific metamorphosed stratigraphic units. Then we have uranium deposits in sandstones, example in Andhra Pradesh and Jharkhand. We have epigenetic but strata bound. Okay, so these are the examples of strata bound deposits. Now we'll talk about concordant and discordant bodies. So concordant bodies are parallel to the layers. Discordant bodies will cross cut the layers. So concordant ore bodies we'll talk about first. Introduction. Concordant ore bodies are mineral deposits that are parallel or conformable with the bedding or layering of the host rock. Right? They occur along planes of stratification and do not disrupt the primary structural feature of the enclosing rocks. So say we have a say any lopolith or locolith, you have studied in igneous petrology. So those are actually concordant in nature. So this is the rock. Say we have a deposit like this. Again we have a deposit like this. This will be concordant in nature, or any rock that have been like this, cross cutting the layers. These are the ore bodies. Okay, these are the ore bodies. So this will be concordant, this will be again concordant, but this is discordant in nature because it is cross cutting the original layers. So formation can occur via syngenetic process where ore minerals are deposited simultaneously with the host rock. Then we have epigenetic process where mineralization occurs later but still along the bedding planes of foliation. So if mineralization occurs afterwards, it has to follow the local beddings and should not disrupt the local beddings. If that happens, then it can form in with syngenetic, okay, along with the formation of rock, and epigenetic, that is post deposition of the rocks. So nature and characteristics, they are typically strata bound. Okay, they are strata bound mostly. That is confined to a specific stratigraphic unit, although not always strictly bed parallel. Okay, but often laterally extensive with uniform thickness. Mineralization follows the original sedimentary or igneous layers. These are especially common in sedimentary or layered metamorphic terrains. Okay, so mostly we see wherever there is a layered terrain, layered rock type, we can find. If there is mineralization, if there is ore bodies present, then that will be mostly strata bound and concordant with the original rock layers. Then we have morphological types, forms, structures of concordant ore bodies. So type and description, we have stratiform, so flat sheet-like ore bodies strictly confined within the single stratigraphic layer. Example, sedimentary copper BIFs. Then we have strata bound, occurs within a particular stratigraphic unit but not necessarily confined to bedding planes. Example, Zawar, lead, and zinc. Then it can be lenticular. Lenticular means like lenses, like this. Okay. So lens shaped bodies, thicker in middle and thinner in edges. Example, some manganese deposits or saucer group. Then tabular sheet like, thick plate like bodies following bedding planes. Example, coal seams, phosphate beds. So these are the examples of the types of deposits and the description. Okay. And they sill like, sill from igneous intrusive ore bodies concordant with layering. Example, chromite in ultramafic sills. Right. Now we will talk about the discordant ore bodies. Discordant ore bodies means discordant ore bodies are mineral deposits that cut across the structural features. Example, bedding foliations of the host rock, unlike concordant bodies which are parallel to them. This is excellent dike, discordant ore body, and this is the previous rock layer. And you can see these are cross-cutting the rock layers. So mode of formation, they typically form through hydrothermal process. Okay, so when upward drafted fluid um, chooses to move in this path and precipitate minerals here, they will form this type of dikes. So where metal-rich fluids fill fractures, faults, or joints and precipitate minerals as they cool, right? So forms and morphological structures. So it can be veins, okay, deposits of mineral filling cracks or fractures in rock. They often occur in a linear fashion and can be quite rich in ore. Example: quartz gold veins. Quartz gold veins are very important, found in Karnataka also. Okay. Loads, large persistent bodies of ore that are generally massive and extend vertically. Okay. Load deposits. Then we have nuggets. Okay. Small pockets. So naturally occurring large piece of metal ore such as gold nuggets. Then stockwork, network of intersecting veins or veinlets that form a stockwork pattern. You know stockwork, like that it can also happen. Then dikes and sills, igneous hosted mineralization. So this is actually a dike. Then pipes or stocks, example, kimberlite pipes for diamonds. So kimberlite occurs as pipes in the rock layers. Okay, they will happen to form like this. And kimberlites are mostly formed in the like at a greater depth due to tectonic activity. They get carried towards the shallower depths. This is a rock body, and kimberlites can be present as this type of pipes. Okay, these are kimberlites. Kimberlite pipes for diamonds. Now nature and characteristics. So it has sharp and discordant contact with host rocks. Variable shapes can be there. It can be tabular, lenticular, or cylindrical, often associated with structural controls. Example: shear zones. Okay, shear zones have gappings. Whenever there is some kind of gappings, be it veins, be it any fracture, be it any fault, if those are actually filled by any hydrothermal fluid, then that will form this type of discordant structures. So economic significance are frequently high grade due to focused fluid flow, require detailed structural mapping for exploration. Example include gold quartz veins, lead zinc sulfide veins, and kimberlite pipes. Right?